Hello everyone, here's your Sioux Falls physics teachers talking about work, and in this case we're looking at work in the physics sense. We have three different situations and we want to calculate the work done in each situation. So let's start here with situation number one. Calculate the work done when a 10 kilogram object is pushed 4 meters at a constant velocity on a frictionless surface. So here's our situation. There's our object. It's being pushed along at a distance of 4 meters. And notice that if it's going at a constant velocity, there's no friction, which therefore means no applied force is needed. Well, our work is equal to force times distance. In this case, the force is 0. So the overall work is 0 for this situation. Now, our next situation, in situation B here, is similar. An object is pushed 4 meters at a constant velocity. However, this time, the surface does have friction. So if we think about pushing the object 4 meters horizontally like this, there is a force of friction opposing that movement, then there must also be an applied force to counteract that friction. So if we can figure out how much friction there is, then that will be the same as the applied force, and that's what we would use to find the work. Now in this case we can sort of do this all together. Work would be equal to the force of friction times the distance. Force of friction is normal times coefficient. In this case, to find the normal, we would use mass times gravity. And then the coefficient was given to us as 0.35. Multiply that times the distance, and that would give us our total for the work. So a 10 kilogram object multiplied times 9.8 for gravity. Coefficient of 0.35. And then finally, looking at our distance of 4 meters, multiplying those all out, and we have a work value of 137 Newton meters, or joules, as the work done in this situation.
All right, now let's look at part C here. In this case now, we're going to take that same 10 kilogram object, and this time we're going to lift it at a constant velocity. So here's my object again, and now we are lifting it upward, all right, at a constant velocity, and again we are going to lift it a distance of 4 meters. So what are the forces acting on that object? Well, we know that, again, if it's a constant velocity, that the net force on it is equal to 0, but we know for a fact that gravity is pulling down on the object. So if I'm going to have a net force of 0, then I must have an applied force in the upward direction that is equal to gravity. So my applied force has to equal my gravitational force. And remember, the whole thing here that we're trying to do is find work. So in this case, work is going to equal my gravitational force times the distance that I lifted, okay? To get the gravitational force, that's again just taking mass of my object times g, and then again I'm going to multiply that by that distance. So plugging my numbers in, I have a mass of 10 kilograms, multiply that by 9.8, and it lifted it 4 meters. Okay, plug all that stuff in, and I get a work value in this case of 392 joules.
Hello everyone, here's your Sioux Falls physics teachers looking at another little twist when we're calculating work. We have a crate pulled across the floor by a rope attached at an angle of 30 degrees. The tension in the rope is 40 newtons. Calculate the work done. Well, in this case, we actually want to draw ourselves a little diagram so we can sort of visualize what's going on. Okay, the crate is moving across the floor 2.4 meters. And then if we think about the force from the rope, okay, the rope has a tension of 40 newtons, but that tension is at an angle of 30 degrees from the horizontal. Now the problem, of course, is that for work, we need to have equal dimensions for the distance and the force. So since our distance is a horizontal distance here, 2.4 across the floor, that means that when we look at this tension of 40 newtons, all we need to use is the horizontal component. So again, that 40 newtons is divided into some force in the x direction and some force in the y direction. The force in the y direction really isn't important to us in this case. So the first thing we need to do then is find the x component of that 40 newtons. The x side is adjacent to 30 degrees, so we would use the cosine of 30 degrees. That is equal to the adjacent side of tx divided by the hypotenuse of 40 newtons, and we get a component in the x direction of 34.6 newtons. So in reality here, out of that 40 newtons, only 34.6 are in the same dimension as our distance of 2.4. When we actually calculate work now, when it says force times distance, the force amount that we want to use is that component that's in the same direction, which is the 34.6. Distance is still 2.4 meters, and that gives us a total work done of 83.1 joules as that crate is pulled across the floor.
Hey, thanks for tuning in to Sioux Falls Physics Teachers. We have a work and kinetic energy problem here. This is a really key example here. This is a big concept, so hopefully this one will help you in learning this. What we're going to look at, we have a 0.05 kilogram particle. It's moving at a pretty fast velocity, 250 meters per second. And then we're going to put a force on that particle to stop it. And the stopping force, we're told, is 10,400 newtons. Now, question we have is how long of a distance does it take for that particle then to come to a stop? All right. So what we're looking at using here is our relationship where we know that the kinetic energy that we start with, I'll call it KE1, all right, has to equal KE2, but there's also some work involved here, right? And so because this particle is moving, right, then we know that there is some work, namely the stopping force that is going to be introduced into this, so that we know at the end, the kinetic energy that we have at the end is essentially going to be zero, because we know that this thing comes to a stop at the end. All right, so essentially what we're going to be saying here is that KE1 plus work has to equal zero energy. So let's start with KE1. We know that that is 1/2 mv squared. So the mass is 0.05, and the velocity that this thing's moving at is 250 meters per second. Now I'm going to add to that some amount of work to get my equation equals zero. Right away we can see by looking at this that we know that our work is going to have to be negative. So all right, let's go ahead and calculate some of this out here. We know this is going to be 1,562.5 joules of kinetic energy that this starts with. All right. Now, the work that we're going to introduce here is going to be equal to the stopping force times that distance. Remember, we are trying to figure out the distance that it takes to stop this thing. So the stopping force they told us was 10,400 newtons. Now this is where we're going to introduce our negative in, because that force is working against the kinetic energy. It's working against the movement of the particle. So I multiply that force times the distance that it takes. That's where I'm getting my work from. And again, we know that this is all set equal to 0. And the reason I know that's set equal to 0 is because this thing is coming to a stop at the end, so it has no kinetic energy at the end. So now we've got an equation here that we can simply solve for D just by doing a little simple algebra. We're going to end up that distance here is going to end up being equal to that 1562.5, all right, divided by our 10,400, okay? And when I do that, I'll end up getting a distance of 0.15 meters.
Well, hello again, everyone. Here we are looking at another example on how work and kinetic energy relate. And again, this is a very, very important relationship between the two. We have a car sitting at a stoplight. The driver applies a net force of 125 newtons. Calculate the velocity of the car after it has traveled 550 meters. Now again, as we've noted on a couple of these, we could do this problem using concepts from back with kinematics and just looking at motion, but as it turns out, it's usually a lot more efficient to do this using energy. We want to think of it this way. To begin with, we have a certain amount of kinetic energy, which in this case is 0 because it is at rest. To change that energy, work was done. So by adding the amount of work, and in this case the work will be a positive value because the work is giving this car more energy, that will then give us our final kinetic energy at the end. So now let's start looking at some numbers, and again it is at rest. So our initial kinetic energy would be 0. Work is found by taking force times distance, and kinetic energy is 1/2 mass times velocity squared. So we have the net force, the force that's doing that work, giving that car more energy, is 125 newtons. The distance traveled during this time was 550 meters. So multiplying those two together will give us our work. And then the mass of the car is 950 kilograms, which leaves the final velocity as our only unknown. And that final velocity is then 12 meters per second. And that would be the velocity of the car after that amount of work has been done.
Hey, this is the Sioux Falls Physics Gang. We are here looking at graphs today, and specifically looking at work from a graph. So as you can see, we have a graph here showing us the displacement and the net force acting on an object, all right? And we have a 1 kilogram object that begins with an initial velocity of 0. That's a key piece of information for us. And they ask us to determine 3 different things from this problem, all right? We are asked to find the acceleration, the kinetic energy, and the velocity when the object's at a position of 4 meters, okay? So on our graph, we are looking at this point right here, okay, when the displacement is at 4 meters, all right? So really, for all practical purposes, we don't really care what's happening after that, all right? So we're only interested in what's happening from when it starts to when it gets to 4 meters. So let's first look at the acceleration, all right? So the acceleration at the point where it's at 4 meters. Because this graph tells us the net force acting on the object, and it is important that we are being told the net force that's acting here, we can really simply just use our F equals ma equation, all right? Because I now know the net force that's acting on it at the 4 meter mark, and that force happens to be 6 newtons. I can look at that off of my graph, and I know the mass of the object that I have is 1 kilogram. All right, so it's pretty easy for me to solve for the acceleration here of 6 meters per second squared.
So that's the acceleration. Now the next two, kinetic energy and velocity, are very closely related to each other. Basically, when we see this graph, remember from our definition of work, work is equal to force multiplied times distance or displacement. And in this particular case, we have those two things on the axes of our graph. So just as a reminder, anytime you see two things multiplied together on a graph, that indicates the area of the force versus displacement graph. So if we are looking here at a distance of 4 meters, basically we need to find the area from 0 to 4. This can be broken down into two shapes. One is a nice tall triangle here at the beginning, and then secondly is a nice tall rectangle. Well, by going through the math there, if we figure out for the triangle part, our area would be 1/2 times the base times the height. Our base is 2 meters. Our height over here is 6. And so if we use 1/2 times base times height, we end up with 6 joules as the area for that portion. Okay, for the rectangle then, area for the rectangle would just be base times height. Our base is again 2, our height is again 6, and so the area for that portion is 12 joules. Okay, that means then that the total area under our graph, which would be the total work that is done, is simply those two added together. So we have 18 joules of work. Now notice that our problem specifically says, what is the kinetic energy? Okay, well, notice one other piece of information. Our object started with an initial velocity of 0. So if we go back to our kinetic energy and work relationship, initial kinetic energy plus work done is equal to final kinetic energy. So if our object begins with an initial velocity of 0 and 18 joules of work has just been done, then that means that the final kinetic energy must be 18 joules, since that is the amount of work that was done on it before it reached 4 meters on the graph. That value can then be used directly for our last piece of information, which is the velocity of the object at that position. Remember that kinetic energy is simply 1/2 times mass times velocity squared. So if we've just found out that we have 18 joules of kinetic energy and the mass of our object is 1 kilogram, which is kind of handy for the math of it, we find out then that our final velocity should be 6 meters per second.
All right, this is a problem on potential energy. Thanks for tuning in, the Sioux Falls physics teachers. This problem, we have a 60 kilogram diver that's standing on a high dive. The high dive happens to be 4 meters above the surface of the water and 7 meters above the bottom of the pool. And so what this problem is asking us to do is to calculate the potential energy that the diver has relative to the surface of the pool and also relative to the bottom of the pool. So let's dive in here to that, no pun intended. And remember, our equation for potential energy looks something like this. Potential energy is equal to the mass of the object times gravity multiplied by its height. Now, again, we have to take into account what we're measuring the height from. So for this first part, we're going to do it relative to the water's surface. So in this case, the potential energy would be the mass of the diver, the 60 kilograms. I'm just going to go ahead and estimate my G in this case as 10 meters per second squared and a height of 4 meters. So just a little simple multiplying all that together, you would get a potential energy of 2,400 joules. Now, that's relative to the water's surface. What about relative to the bottom of the pool here? Okay, the second part of this. Well, before we calculate it, let's just use our intuition. We expect that potential energy to be more or less. All right, well, we would certainly expect it to be more in this case because we know that the height that we're talking about here is now greater. So in this case, relative to the bottom of the pool, we still have the same 60 kilogram diver and the same pull of gravity, or the same acceleration due to gravity, but now our height relative to our zero line is 7 meters. And so when I calculate that out, I get a potential energy of 4,200 joules. So a key thing to remember is that potential energy is measured relative to a point or to a reference point. So you can see here, you could say that this diver has two different possible potential energies. It certainly matters what reference point or what zero line we are referencing that potential energy to.